Yeah, so what's the problem with distances that grow? Well, yeah, as I just said, I mean, if we have more features, which means we have more to sum up, yeah, for example, in the Euclidean distance, then of course we get higher values. So here's an example for that. So we just use the Euclidean distance, which is used very often, of course, yeah, and we have these vectors here, two-dimensional vectors, 1, 2, which is A here, and B, 4, 3 here, and the Euclidean distance, of course, between A and B is this vector here, yeah, which is in that case square root of 10 if you just compute it, like 1 minus 4 squared plus 2 minus not 3 but 4, not 4 but 3, because it's 4, 3 here, sorry for that, squared, and so on and so on. Yeah. Yeah, so which corresponds to the norm of this difference vector here, of course, which is 3, 1 in that case. Yeah, very good. Everything's fine. But now what happens actually if we increase the dimensionality is, of course, that the distances grow too. So if we just double the feature vector length, yeah, so we take the original feature vectors 1, 2, and 4, 3, and just pump them up, double them, so to say. So we have 1, 2, 1, 2 now, and 4, 3, 4, 3 now. Now we get double the length of the original feature vector. Yeah, so we have now a square root of 20 instead of a square root of 10 as before. Yeah, so obviously just pumping up or doubling the size of the feature vectors, meaning that we somehow double the size of the distance values, so to say. Yeah, and again, the effect seems not so important. Just the values may only scale a little larger. No, that's actually not the case, because larger values also mean that the contrast between the values, between individual values, is slowly lost as the distances grow, the values for the distances grow. So, and that grows with growing dimensionality. So the higher the dimensionality is, the higher are the values for the individual distances, and the lower is the contrast between the distances, just numerical. Yeah, and that is known as the so-called concentration of distances problem, which we will actually talk about next on the next slide. Yeah, but that's the main course and the main point, that with increasing values, so if all the values get larger, the absolute contrast between the distances is typically lost. Yeah. Because everything grows more or less in the same way. So here's the concentration of distances problem, which says that as the dimensionality grows, the distances or the distant values grow too, such that the numerical contrast provided by usual distance measures decreases, yeah, or even diminishes, yeah, even becomes zero. Yeah? So we cannot distinguish points or patterns based on distances anymore. Yeah, so that is, in other words, the distribution of norms in a given distribution of points tends to concentrate. And again, here is an example for Euclidean distances or Euclidean norms of vectors, which is basically, I mean, the Euclidean norm here is that what we compute when we compute the difference or the distance, the Euclidean distance between 2 points, is basically the norm of the difference vector. So we are interested, or it's important if something happens with this norm of the vectors if dimensionality grows. And that's exactly what happens. Yeah? So the Euclidean norm of vectors consists, of course, of several variables that are independent, at least assumed to be independent, and identically distributed. Yeah? So we have something like the norm of vector y is the first feature of y, the value of the first feature of y squared plus this value of the second feature of y squared plus the dth value, of course, of feature of the dth feature of y squared, and then the square root. Yeah, and this norm actually, and that's what the concentration phenomenon or the concentration of distance problem says, behaves extremely unexpectedly, and we'll see how. So there is a theorem about this concentration of distance phenomenon that says, okay, we have a d-dimensional vector y with d components. All components are assumed to be independent and identically distributed, which is not such a limiting assumption. well, what happens, the mean and the variance of the Euclidean norm, which is, this is the mean of the Euclidean norm, yeah, and this is the standard deviation or the variance of the Euclidean norm, are fixed, so to say, yeah, depend only on parameters A and B that only depend on central moments of the order 1, 2, 3, 4. Yeah? So in other words, the norm grows proportionally to, what do we have? We have A and B that are parameters that are somehow constant, yeah? Or at least depend on central moments of some constant. And then we have D here and D here, which is the dimensionality of the data. Yeah? So that is actually growing. Yeah? So if the norm grows, if D grows, the norm also grows proportionally to square root of D. Yeah? So that remains here as the major point. But the variance, if we look at the variance also grows here, and actually it grows, doesn't grow actually, but remains the same, because the limit of D to the power of some constant is actually 0. Yeah? So for large D, the variance here, this one here, remains the same for large D here. Yeah? B is a constant, A and B are constants more or less. So the norm, the expected value of the norms grow with dimensionality by a kind of linear factor or square root of D factor. But the variance actually remains the same, meaning that, okay, actually that's exactly the point, but what we just said, the values increase, yeah, the values get larger, but the relative contrast between them, between the individual values, the variance, yeah, remains more or less the same. And that's exactly what stated before, that we lose contrast among the different distances. Yeah? And that is something which is not really nice. Yeah? So with growing dimensionality, the relative error made by just taking the expected norm instead of the real norm becomes neglectable, because, well, the norm grows, but the variances doesn't grow. Yeah? It diminishes to 0. So in that case, if the variance is 0, we can just take the expected value, yeah, the mean value, instead of the real value, because the variance is close to 0. So we don't make a real error if we just take the expected value instead of the real value. Yeah? Because expected value and real value are more or less the same in most of the cases, because of the variance being 0. Yeah? So and that is exactly the point, that well, if D grows, the differences between the individual distances between pairs of points are more or less the same. Yeah? The difference just decreases. So there is no way to differentiate between pairs of points based on their particular distances. And that is not a good story, right? And that is not a good result.